Hello everyone, welcome to this class on diffraction of light. So Huygens theory proposed regarding the nature of the light, which is wave theory of the light. According to Huygens, the light also shows the phenomenon of diffraction, which is possible only when light can behave as a wave and not just like as shown by the ray theory of light proposed by Newton, which is ray theory of light, right? That according to that theory, ray theory of light travels along a straight line just like that. So Huygens said that if this is the case, then he took two situations. There is the first situation whenever there is some source of light and there is some opening. So there is some opening in front of this source of light through which the light is entering the opening, right? So in front of it we have placed a screen. So what just he said that if light travels just like along a straight line, then it should have illuminated this region, only this region, right? So at the edges the light ray will go straight and it will just illuminate this region. But actually what is happening there, that light ray is slightly bending at the edges of this opening, right? Due to this bending, the light ray is covering a larger portion of the screen, or we can say the light is bending around the corners of this opening and hence illuminating a larger portion of the screen. So when light bends, it is not the property of a ray but a property of the wave. So when light can behave as a wave, only then it can just show this bending around the edges of this opening or slit. Similar case is observed whenever in place of this opening there was an object, right? The size of this object and this opening, this should be smaller enough, right? So small that it is comparable to the wavelength of the light being used, right? So in this second situation, whenever in place of this opening we have some object, if light travels along a straight line in the form of rays, then it should illuminate this portion of the screen given by this line. In this portion there should be completely darkness, but actually what is happening, the light ray is again bending around the edges of this object, or we can say corners of this object, and it is bending and therefore illuminating a larger portion of the screen. So it is giving rise to more portion of the screen which is illuminated. So both of these behaviors of the light shown by the light, Huygens concluded from here that light should not be traveling just like a ray, but it should be traveling just like a wave. And then he proposed this phenomena as the diffraction of the light. So he defined the diffraction of the light as the phenomena of bending of the light around the corners and the encroachment of the light. Just you must remember only the phenomena bending of light around the corners or edges of the objects and hence illuminating a larger portion of the screen. You can remember this in that way. That will be easy to remember. So this is what diffraction of light is according to Huygens as observed in these two situations. Now he proposed that there are two ways in which this diffraction can be understood. First one is called as the Fresnel diffraction. In this kind of diffraction, what happens? This kind of diffraction is observed when both source and screen, source of the light and the screen where the diffraction pattern is observed, both of them lie at a finite distance from the slit. Slit means opening. Here we will make use of a fine opening called as slit, as we have taken in case of interference of the light waves. So in Fresnel diffraction, source as well as screen, both of them lie at the finite distance from the slit or from that opening from which the light coming is creating a diffraction pattern, right? So if source is at a finite distance, that means it will be producing spherical wavefronts or cylindrical wavefronts, depending upon whether the source is a point source or a line source. Here we suppose that it is a point source, so it will be producing spherical wavefronts. other kind of diffraction, it is called as Fraunhofer diffraction. It is also called single slit experiment. In this case, both source and screen are placed at infinite distance in order to observe this kind of diffraction. Why the source and screen are placed at infinite distance from the slit? It is because we require the plane wavefronts to study this kind of diffraction, right? So in order to get the plane wavefronts, we have to keep the source and the screen both at infinite distance from the slit or from the opening from where the light coming is producing the diffraction pattern on the screen. So that's why these has to be placed at infinite distances, right? So if it is an experiment, then in laboratory there is nothing like infinite distance. We can't do that. So in order to do that, what we do, we place the source at some finite distance. For example, a point source which will produce the spherical wavefronts. To understand the situation well, let us take this diagram as we have discussed earlier. So in this case, the parallel wavefront, light in the form of parallel wavefront, it is approaching the convex lens, and after passing through the convex lens, we are getting spherical wavefronts, spherical converging wavefronts, right? We consider the opposite of it. Suppose that here at this point, if we are placing a point source, so it will be producing spherical wavefronts. So that means the spherical wavefronts are approaching the lens, right? So after passing through the lens, they will be converted by this convex lens into the plane wavefronts. That means in laboratory conditions, in order to achieve the plane wavefronts, what we do, we take a point source of light which will produce the spherical wavefronts, and in front of that source we place a convex lens so that the source is at focus of this convex lens. So when these spherical wavefronts enter the convex lens, and convex lens make these spherical wavefronts into plane wavefronts, and therefore we are getting the plane wavefronts in order to observe this Fraunhofer diffraction. Similarly, screen cannot be placed at infinite distance to achieve a diffraction pattern. So therefore we place the screen at a finite distance from the we can say slit, and in order to observe the pattern, diffraction pattern in front of the slit, we again place another convex lens. So situation is here, we place another convex lens which just converges all these plane wavefronts coming from this slit, or we can say opening on the screen. So this is Fraunhofer diffraction, or it is also called as the single slit diffraction. So this is very important from exam point of view. One must understand it very carefully. There are a lot of terms which are very similar to the interference of the light. So this is a single slit experiment for the diffraction of the light. So what is the situation here? We are getting plane wavefronts as we have just discussed now. In front of single source of light or point source of light, we are placing a convex lens which produces the plane wavefronts, right? So here we take that light is approaching this slit AB. It is the slit AB, right? It is the opening, fine opening, very fine opening. So these plane wavefronts coming after this convex lens, they are approaching this slit. So these plane wavefronts are illuminating each and every point of this opening, right? Or we can say slit. With the light, or we can say these points illuminated, they are not just 12, but there are infinite number of points which are illuminated by the these plane wavefronts of the slit. So the light coming from this slit, or we can say light coming from different sections of the slit, they just interfere, these light beams interfere, and they produce some dark or bright fringe on the screen, depending upon whether they are interfering constructively or destructively. So in general, we can say that in diffraction pattern, these dark and bright fringes on the screen are achieved with at the center a bright fringe due to the interference of the light waves coming from different sections of this slit. So this is what we observe in case of diffraction at a diffraction of light at a single slit. So this is the very simple diagram to remember. So the light is coming from different sections of this slit which is interfering with each other and hence producing the dark and bright fringes at different locations on the screen with a bright fringe at the center of the screen. So what is happening? That the light coming from the different section, because each and every point of this slit is illuminated. So each and every point of this slit act as the source of secondary wavefronts. So that means each and every point is emitting the light in forward direction. So the light coming from different sections of this slit, they just interfere and produce a diffraction pattern of bright and dark fringes on the screen with bright fringe at the center of the screen. So how does it happen? The light coming from different sections interfere at a point on the screen either constructively or destructively. It depends upon the path difference between the lights coming from different sections of the slit. So it depends upon the path difference of the lights coming from different sections of the slit. So if the path difference is 1, it may be a dark fringe. If the path difference is other, it may be a bright fringe, right? So due to the interference of the light waves coming from different sections of this slit, different portions of this slit, these just interfere constructively and destructively and hence produce diffraction pattern. At the center of screen, they just interfere constructively and hence produce a bright fringe where the intensity of light is maximum. And then as we move away from the slit, we get a dark fringe at position P1, for example, on either side. It will be the position of the dark fringe because at this point the light coming from different sections of this slit, it will just interfere destructively, and beyond that, so here intensity of the light will be minimum, and beyond that, or we can say just next to it, there will be a bright fringe again because the path difference between the light waves coming from different sections, it will be such that the light waves just interfere again constructively in order to give rise to a bright fringe. So alternate dark and bright fringes are formed on both sides of this central bright fringe. Here, slight difference from the interference of the light waves as we have discussed in case of Young's double slit experiment is that the intensity of the central bright fringe, it is maximum, and the intensity of successive bright fringes goes on decreasing, where in case of interference pattern, as shown in case of Young's double slit experiment, we see that all the bright fringes, whether it is the central bright fringe or successive bright fringes, all are of equal intensity. So this is the difference between the Young's double slit experiment on interference of the light and single slit experiment on the diffraction of the light. So that's why on this side, this is nothing but the graph for the intensity of the light. In this direction, we are taking intensity, and along this direction, we are taking the distance of the points from the center of the screen. Now we can extend our discussion to find out the conditions for a point to be the position of a dark fringe or a bright fringe. So for doing that, what we do, we take this diagram, which is same as we have just discussed. For simplification, we are just taking only 2 sections of this diagram. Similarly, we can take 3 sections, 4 sections, 5 sections or so. So here, the plane wavefronts are approaching this slit, which is of dimensions d. This is the width of this slit, right? It may be d or it may be anything else which you can take easy to remember. So the light is coming from different sections of the slit. It is, suppose that we are taking some point P1, which may be the position of a dark or a bright fringe, right? So here the light coming from section first point A and the light coming from the final point B, they are converging at point P1, right? So there is a path difference which we can just draw by showing this perpendicular. So we are drawing a perpendicular from this point A on this line. It is B P1. So this is the line on which perpendicular is drawn, which meets this line, the light coming from the extreme point B of this slit, and it meets this perpendicular meets this line at point N. So it is perpendicular here. So that means the distance covered A P1 is less than the distance covered B P1. That means the light coming from this lower point it is traveling this much of extra distance given by Bn. So how much is this Bn? We will find the conditions according to this path difference, right? So for finding Bn, what we do, we just take this right angle triangle ABN. So when we take this triangle, we see that Bn, in this triangle we just find sine theta, right? So here, if this angle is, for example, theta, because it is taking some bending due to this path difference, or we can say this lens is tilted, or the light ray coming from the center to reach point P1 makes an angle theta with the line joining the center of the screen and the center of the slit. So this angle is theta. So if this angle is theta, this angle will also be theta, this angle. So this angle BAN, it will also be equal to theta. So in this triangle ABN, where this angle A means BAN is theta also, for the center of screen it will be 0. But for, if this angle is theta, this angle will also be theta. So sine theta from here, it becomes equal to Bn upon D, right? So it is Bn upon D, means perpendicular divided by hypotenuse. So from there we can calculate Bn. So from here Bn comes out to be D times sine theta. So Bn is the path difference for the light coming from the two extreme points of the slit. So these are the two extreme points, A and B. So light coming from A, it is having path difference with the light coming from point B, which is equal to Bn. And if there is some midpoint of this slit, then the light coming from this point will have the path difference, which will be half, because this is the midpoint of this slit. So in order to find out the condition for the minimum, we suppose that the path difference is equal to, in first case, we take that the path difference, point P is such that the path difference between the light coming from point A and B, this path difference, it is equal to 1 lambda. So if this Bn is equal to 1 lambda, means lambda, then the point P, it will be the position of the dark fringe, right? So it will be the position of the dark fringe. How does that happen? So let us write the expression first. Because Bn means path difference, it is equal to 1 lambda. So it is given by D sine theta. Here we take, for first dark fringe, we take the angle to be theta 1, right? So how does, for this path difference, there will be a dark fringe at point P1? It can be understood in the way that, suppose that slit, it is divided into two equal parts. If we divide this slit into two equal parts, the upper half of the slit and the lower half of the slit are identical. Now the light coming from upper half and the light coming from the lower half, they will be interfering destructively, because they will have the path difference which is given by lambda by 2. This total path difference is lambda, but half of the slit, it will have the path difference lambda by 2. That means the light coming from the upper half, it will its crest will be at point P1, for example. Then from the lower half, the light coming, it will have its trough at the point. So therefore they will interfere destructively, and hence there will be no portion of the slit from which the light coming is illuminating point P. Because the light coming from upper half, it is cancelled by the light coming from the lower half. So there is no portion of the light from where the light coming can illuminate point P1. So therefore point P1, it will be the position of the dark fringe. Similarly, if this path difference Bn, P1 point is such that this path difference Bn, it is equal to twice of lambda. In that case, again, we will get next minima, or we can say dark fringe, the next dark fringe. It will be such that, so let us just solve this first. So from here, because Bn is equal to 2 lambda, so we can say that 2 lambda is equal to D sine theta 1, because it will be a theta 2, it will be a different angle, because point P1, it is P1, now it will be the second dark fringe which will be at successive position. So angle theta will be different for that one. So that's why we are keeping it theta 2, which is different from theta 1. So therefore we get this expression D sine theta 2 which is equal to twice of lambda. So we are getting an next dark fringe. It will be the position of the dark fringe also, because in order to understand that, we suppose that this slit is divided into 4 equal parts. So when this slit is divided into 4 equal parts, the corresponding parts, for example first and fourth, they just cancel the effect of each other. The light coming from first section, it will be cancelled by the light coming from the last section, means fourth section. And then the light coming from second section, it will be cancelled by the light coming from the third section. Again, there is no other section of the slit which is left from where the light can come and illuminate this second point P. So therefore, if the path difference is twice of lambda, again we get a dark fringe. It is called as secondary minima or second dark fringe. Similarly, we can generalize if the path difference Bn, it is equal to n times lambda, where n goes from 1 to 3 and so on, then it will be the position of nth secondary minima, right? It will be the first secondary minima, or we can say dark fringe. It will be the second secondary minima. It will be the nth minima, right? Secondary minima. So this is the expression for it. So because the distance between slit and screen, this screen and slit, it remains quite small. So therefore this angle theta 1 or theta n in general, this remains quite small. So this remains quite small. So that means these values sin theta 1, sin theta 2, or in general sin theta n, this is very nearly equal to theta n. So therefore from here we get d theta n is equal to n times lambda, and from there we get the condition for theta n for the point P1 to be the position of the dark fringe, or the point of minimum intensity, or the point of destructive interference. It is given for n values of n to be 1, 2, 3 and so on. So theta n is equal to n lambda upon small d. So what just we have did here to find out the condition or right expression for the path difference for the destructive interference or minima, we just considered the light coming from different sections of the slit. From upper point, the light coming is having a path difference equal to Bn with the light coming from the lowermost point. So this is the total path difference the light can have coming from this slit. Then we just considered that if this path difference Bn, which is given by d sin theta, if this Bn path difference, it is equal to 1 wavelength, 2 wavelength, or 3 wavelength, or in general n times of the wavelength, then on the screen at every point of that we will receive a dark fringe or secondary minima. All those points which will have the path difference, they will have the secondary minima on the screen. And from there we come to this expression, because the angle theta remains quite small, so theta n is very nearly equal to sin theta n. So in place of sin theta n, we are just writing theta n, and hence we get this expression. Similarly, we can proceed for finding the positions of the, or we can say conditions for the maxima, the points of brightness or points of bright fringes on the screen. So in that case, we suppose that this path difference, this remains the common expression, this path difference here, in this path difference, it is equal to 3 times of lambda by 2. The path difference is 3 times lambda by 2. Then this 3 lambda by 2, it is equal to d sin theta 1 dash, because it will be the position of the bright fringe. If path difference is 3 lambda by 2, or 5 lambda by 2, or 7 lambda by 2, or 9 lambda by 2, or in general 2n plus 1 times of lambda by 2, in that case on the screen we will get a bright spot. So how do we get a bright spot? How we can understand that? To understand that, we suppose that, for example, the first case of path difference, which is 3 lambda by 2, in this case we suppose the screen is divided into 3 equal parts. So when this, not screen but slit, this slit is divided into 3 equal parts, out of which 2 parts just cancel each other whenever they reach at point P1 on the screen. The light coming from the third part of the, out of the 3, two just cancels each other, but the light coming from the third part, it remains uncancelled and hence illuminate the point P1 on the screen. So therefore point P1 will be the position of the bright fringe. So this is how we understand that whenever path difference is thrice lambda by 2, there will be a bright spot on the screen. So it will be called as the first secondary maxima. And when path difference is 5 lambda by 2, we can suppose this slit to be divided into 5 equal parts, out of which 4 parts just cancels each other, and the remaining the light coming from the remaining fifth part, it will be the only which will be illuminating the point on the screen, and hence that point on the screen will be the bright position of the bright fringe, right? So this is how we understand how the secondary maxima are formed. So in general we can write that d sine theta n dash, from here we have written is in general expression d sine theta n dash, because these theta n means angles are the angular positions of these bright fringes, or we can say maxima. This will be equal to 2n plus 1 lambda by 2. Again, because these angles remain small, so sine theta n dash, it is just equal to theta n dash. So therefore on the left hand side it is d theta n dash, which is equal to 2n plus 1 lambda by 2, and from there we get the condition on this angle for the position of the maxima, that theta n dash, it is equal to 2n plus 1 lambda upon 2d, where n goes again from 1, 2, 3 and so on. So this was about finding the conditions for the secondary minima, means dark fringes, and secondary maxima, means the bright fringes. Now we can proceed in order to find out their positions, right, and their widths. So for that, what we do, on the screen suppose we have point P1 which is at distance y1 from the center of the screen. So in this triangle, here this point may be taken as C, so it will be C P1O. In this right angle triangle, we will find tan theta 1. So tan theta 1, it will be equal to perpendicular P1O, which is y1, divided by this CO, which will be equal to D. So therefore tan theta 1 is equal to y1 upon D, right? And again, because angles remain quite small, so tan theta 1 is very nearly equal to theta 1. So from here theta 1 becomes equal to y1 upon capital D. And we just have calculated theta 1. So theta 1, it is given by, from here it will be given by theta 1, it will be equal to 1 times lambda upon small d, means lambda upon d. So from there we take the value of theta 1 to be lambda upon d and substitute this value here. On substituting this value of theta 1 to be lambda upon small d here in this expression, we can get the value of y1, the position of the minima, the position of the first minima, which is given by, from here y1 it will be equal to, we take the d to the other side, so it just multiplies this. So it will be d, capital D, lambda upon small d. Here capital D is, it is the distance between slit and the screen, and small d, it is the size of this slit, right? So we can understand the effect that if d means small d is smaller, the position of these dark fringes will be at a farther point. That means the diffraction pattern will spread at a long, and hence it will just spread over the screen for a large range. Similarly, if capital D is less, this slit, or we can say screen, is placed close, then this pattern will be over a small range of the screen. And wavelength, if we use the light of a larger wavelength, then we see that the diffraction pattern will spread over a large area on the screen. And if the wavelength of the light is less, then it will spread over the smaller area of the screen. So wavelength is less, distance of the fringes, dark and bright fringes, will be less. Or let us take this is case of the dark fringes, or we can say minima, right? Similarly, we can find out if point P1 it is the position of the second dark fringe, then it will be theta 2 here, and from there we can just write according to the expression. So theta 2, it will be equal to 2 lambda upon d from here. theta 2 it will be possible for n is equal to 2, so it will be 2 lambda upon d. So when we substitute theta 2 we will get y2 which will be equal to twice, here we will get 2 d lambda upon small d. So that will be the position of the second minima or second dark fringe. So in general we can write the expression for the nth dark fringe as yn, which will be equal to n d lambda upon d, just as this. So this is the general result which we can use in order to calculate any number of dark fringe or the secondary minima on the screen. So for 50th, for example, for 50th dark fringe, we can just substitute the value of n to be 50 and we will get the position, or we can say distance of that 50th dark fringe from the screen by using this formula. And we already know that between any two successive dark fringes there will be maxima, right? So by finding the difference between the positions of any two successive dark fringes, we can find out the width of the bright fringes. So the width of the bright fringes, it will come out to be, if you find the difference, it will come out to be d lambda upon d. For the first bright fringe, for the second bright fringe, or for the third bright fringe, for all of them the width will come out to be d lambda upon d. So when we find the difference between the positions of the any two successive dark fringes, we will get the width of the bright fringe. Whatever we will get, it will be the region over which the bright fringe will be spread, right? So it will be the general expression for the position, for the widths of all the bright fringes. So all the bright fringes will be of same length because this expression is independent of n. And the central bright fringe, it will be spread on the either side of the center of the screen. So it will be twice of the width of the successive secondary bright fringes. So if the central maxima is taken as b naught, or we can say central bright fringe is taken as b naught, it will be twice of this width. That means the central bright fringe, it will be double the size, or we can say width, than the all other bright fringes. Similarly, very similarly, we can do the calculation and derive the expression for the widths of all dark fringes and the position of the bright fringes. For that, we take that point P1, it is the position of the bright fringe, for which it is angle theta 1 dash. So therefore, it will be tan theta 1 dash, which will be given by y1 dash divided by capital D. Everything is same, only that the situation different is that if point P, it is the position of the bright fringe, then the expression will become in terms of dashes, just as we have discussed here in our previous expression. So it is theta 1 dash here, theta 2 dash here, and similarly theta n dash here. So here we take it to be dash, and the positions of the angular positions of the bright fringes. And from this expression we can get any value of theta n dash. That is for the first bright fringe, or for the second bright fringe, or for the any other bright fringe. So in general expression, by using the value of theta n from here, we can substitute it here because angles remain quite small. So therefore from there we can calculate the y n dash, the positions of the bright fringes, which will be equal to 2n plus 1 into d lambda upon 2d. It will be 2d here, right? So that will be the positions of the all bright fringes, and between any two successive bright fringes there will be the dark fringe. So by finding the difference between the positions of any two successive bright fringes, we can calculate the width of the dark fringes, which will come out to be same. So the width of all dark fringes will also be same. It will be d lambda upon d. So this is how we calculate the widths of central bright fringe, and the width of the other bright fringes, and the width of the dark fringes. So central bright fringe, it is twice of the width of all other dark fringes and bright fringes, and all dark and bright fringes are equal in size. However, the intensity of the light in successive bright fringes, it goes on decreasing. as we have just observed in this case. And why this intensity of the central bright fringe is maximum and it goes on decreasing for successive bright fringes? It is because at the center of the screen, all the light coming from different sections of the slit, they just interfere constructively and hence give rise to a bright fringe at the center of the screen. And successive bright fringes are less in the intensity. This is because lesser and lesser portion for the successive bright fringes, lesser and lesser portion of the slit is illuminating the bright fringes, the positions of the bright fringes. For the first bright fringe, it is only the one part out of the three which is illuminating this point P1. So therefore the intensity of the light is due to only one part of the slit. At the center of the screen, it was the whole slit, light coming from the whole slit, which is illuminating this center of the screen. Now it is only the one of the three parts. And for the next bright fringe, it is only the one part of the five parts, so which will be even smaller. So there is less amount of light coming from the fifth part of the light, which is illuminating the next bright fringe, and hence it is having the intensity which is further less. So that's why the successive bright fringes are having lesser and lesser intensities. So this is all about the dark and bright fringes, their conditions of formation and their distances from the center of the screen and the width of these dark and bright fringes and the central bright fringe, central maxima. You can check the effect on these distances, conditions and these widths due to these parameters. Capital D, the distance of screen from the slit. The lambda means wavelength of the light being used. And the small d means the size of the slit. You can check the difference of all these factors. One last thing regarding diffraction left out is that the Fresnel distance. So what is Fresnel distance? It is that distance. Fresnel distance is the distance from the slit. It is the distance from the slit at which, when the distance from the slit is such that at which the spreading of the light due to diffraction at the center of the screen, it becomes equal to the size of the slit itself. Let me just pose this picture again. So Fresnel distance is the distance of the screen from the slit, so that means D. It will be so that the spreading of the light for the central bright fringe. So for that, let me pose this picture. So it is the central bright fringe. The spreading of the light from the center of the screen, it will be this spreading, this range. This distance, it will be equal to size of the slit, which is D. So that distance, because this will change, as we have discussed here, this distance, it will change depending upon D and capital D. So at particular distance of D, the spreading of the light, this spreading of the light from the center of the screen, this spreading of the light, it will be equal to size of the slit, right? So at D, distance of the screen from the slit at equal to Fresnel distance, which is written as DF here. In some books, it is written as ZF. So there is no difference, that is just symbol. So at this value of distance of screen from the slit called as Fresnel distance, the spreading of the light. So light is spread up to this distance from the center of the screen on the either side, right? So on one side it is spread equal to this. So this one is equal to, at Fresnel distance, this is equal to the size of the slit, which is D, the small d. So therefore we substitute D to be DF, means Fresnel distance, or ZF, and Y1 to be small d. So from there Y1 it is small d and it is DF lambda upon D. So from there DF becomes equal to D square upon lambda. So if the distance D, means the distance of the screen from the slit, is less than the Fresnel distance, there will be no diffraction pattern. So this is the minimum distance that must be obeyed. Now we can just sum up the difference between interference of the light waves and diffraction shown by the light waves. Interference. Interference is due to the superposition of two different waves or trains coming from the coherent sources of the light, whereas diffraction, it is due to the superposition of the secondary wavelets coming from the different parts of the same wavefronts. Which is, what is the same wavefront here? The wavefront which is in the slit. So this is the first difference. Another difference is that fringe width is of all the fringes in case of interference pattern in Young's double slit experiment, all of them fringe width is same. Whereas in case of diffraction pattern, the fringes are of different widths, because central bright fringe, it is of twice the size than the widths of the all other dark and bright fringes. Third difference is that all maxima have the same intensity. All the bright fringes are of equal brightness in case of interference pattern, as we have discussed in Young's double slit experiment. Whereas in case of diffraction pattern, we have just studied that the maxima, intensity of the maxima goes on decreasing. Another difference is that there is a good contrast between maxima and minima. Of course, the sources for that light emission of that light should be coherent. So if the sources are coherent, right, in that case there will be a good contrast between the maxima and minima. That means the bright fringes will be completely bright and dark fringes will be completely dark. But in case of diffraction pattern, there is a poor contrast, because bright fringes, they are bright at the center. As we move from away from the center of a bright fringe, the intensity goes on decreasing and it becomes minimum, right, as the case is here. So these are some differences between the interference and diffraction pattern. So that is all about this topic on wave theory of light. That's all. Thank you.